Hi, I'm Joseph Calabro, and this is my video for the Maths and Advanced AI coursework. So, the first question in the coursework was the LU decomposition of a matrix. So, I can show off how I worked out here. This is the working out. I included this with the coursework, so I don't think I even need to show this off here. But I can show you the program version. This was done through the tutorials. So we were given this decomposition script and the Doolittle algorithm. So it takes in a variable matrix that is defined in the Unity in the inspector here. So these are the values that are from the from the coursework brief. And yeah, it goes through the Doolittle algorithm and it prints out to the screen the resulting matrix. So the L and the U matrix, the A matrix, and the final X result for X. Let me show that off. So if I run the program, okay, and go to the console, so you can see the A matrix, L and the U, the result matrix, the X matrix, and the decomposition, so the L and the U. Okay, and then the second part of question 1 was update the program so that the system can check for submatrix determinants. If any is 0, perform a reordering of the invertible matrix so that the LU decomposition can be processed. Demonstrate the results in the following system. And so this is hard programmed in here. So this is the matrix in the brief. And so this is an if loop that uses the function I made is submatrix determinant 0. So if that equals true, then it will do the LU decomposition. So yeah, so it takes a 3x3 matrix. It only works with a 3x3 matrix because I wasn't able to get it to work with anything higher, and I just got it to work with the example in the coursework. So let me find that in the code. So is submatrix determinant 0. It takes a matrix. It takes an integer for the length of the matrix, and it creates temporary variables, and it basically checks every adjacent section in the matrix. So it basically looks at the submatrices within that matrix and figures out if it's if the determinant is 0. Basically, if it is, returns true here, and if it isn't, then it will reorder the matrix, which is done here actually in this function. So the reorder matrix, it has a while loop that checks with this function. So when this is true, so when it does have a determinant of 0, it finishes the while loop, and it will basically keep reshuffling it until it does find a determinant of 0, but for a set amount of time. So it will break out if it can't find one, if the count reaches a value that's too high. So yeah, so it doesn't infinitely loop because there isn't a determinant of 0 possible in that situation. And I can show you the results of that one as well. So here's the final reordered matrix. Oops, here it is. And then here's the resulting LU matrices. Okay, cool. So that's question 1. Question 2 was just a quadratic equation. I can show off this had to be written down, so this is the solution to it. That's also included in the coursework I submitted. Question 3 was to determine, given the following parametric equations, determine if particles will collide and will the paths traced out over time intersect. So I don't know if you were supposed to write it down, like solve it like this, but I did it anyway. So the paths do intersect because in 2 instances they have the same values, but it's not at the same time, so they do not collide. And I've done this through code as well. So parametric simulation takes 2 vector 3s, R1, R2, which are basically the x, y, and z are found out through the equations given in the coursework brief. So t squared, t cubed, 1 plus 2 times t, 1 plus 6 times t, and 1 plus 14 times t. And so I print using debug.log to the console what this function returns, which is a string. So this simulate function takes an increment amount, which is how much we want to increment t by every single frame, and then a float for the simulation length, so how many times we want to increment that. So we give it value of 0.5 and 50. So this for loop will start at 0. It will simulate it will simulate the whole parametric equation until it reaches I equals 50, and it will increment I by 0.5 every single frame, every loop. So it works out what x, y, and z are for each of these equations, each loop, and then it adds that to the string out, which is created here, temporary variable within this function, and then it returns that string and then prints it to the console. Okay, and I can show that off here as well. This is at the very top. So these are all the results for that. So when it's 0, it's 0, 0, 0, and 1, 1, 1, and then yeah, so this is the whole simulation for that question. I can show off. We were told to make an Excel file as well. So this shows here where they intersect, and here, because they're not in the same row, there's no collision, and there's just an intersection with the paths. Okay, cool. So next was the big question, question 4. So let me go to the other scene. Okay. So for this, we needed to generate terrain. Okay, how should I show this off? So I'll just run it. Okay, I'll show off this first. So in the inspector, we have all the scripts for setting this up. So we have a reference to the player and grid set up. Here I have it by default, a 50 by 50 grid. The cell is a reference to each section of the grid. So that's scaled by 2. Here is a reference to the prefab for that section. Then a material for the wall and for the tiles. And this is the parallel noise setup, so we can choose the scale and an X and Y offset for that, and a height cutoff, so that determines what is a wall and what is a floor. And then there's a height scaler for the walls, so we can make them very big, like very tall, but we just have it for 1 here. And then a purple material for tile 1 and a red one for tile 2. So that's for basically a checkered pattern on the walls. We have that for the floor as well, but with different colors. And then the object setup, we can have a percentage for the chance of spawning an object, and then we have different types of objects. We have collectibles and environment objects, and those are broken down into 4 categories. So we have a collectible, like an orb that the player can pick up, and a key. So an orb and a key object, and then in the environment we have pillars and chess pieces. And these are later clustered, and this is where you can set up the clustering as well. So is clustering enabled, and the number of clusters, so the number of centroids for the clustering for the k-means algorithm. And then the Pathfinder, it's used for checking if items can be spawned. So if the player is able to get to those items, they're going to be spawned. And if the player can't reach those items, then they're not going to be spawned. And we can perform a test here, so we can put it starts at the player's start position, and we can put end X and end Y, and then it will simulate a path and show that visually for us. But let me first show off the program. It might take a hot second to load because the clustering sometimes fails. It fails to get one of each object type within each cluster. So what it will do in that situation is it will delete all the objects, and then it will generate them all again, and then generate the clusters again, and see if one of each object type is within each cluster. If it doesn't find one of each object, then it will just repeat again, and it will continuously do that until it is successful. Okay, this is taking longer than it should, so I might have to cut the video. Okay, here we go. Nice. So let me show off a zoom out first. So this is the environment. As you can see, there's parallel noise to make the walls. I can show off the how customizable that is. And this is where the player starts. And as you can see, these are the orbs. So the orb object, a key object, a pillar object, and let me find a chess piece. Here we go. So, and a chess piece here. So each cluster has to have one of each of those objects within them, just for a clean looking environment. So yeah. And yeah, I can play, and I can run around the environment, collect pickups, collect keys, and yeah. So this is the generated environment. Let me show off some of the parallel noise in action. So if I disable clustering, because that makes it load for a while, just so I can show this off, let me show off the path actually. So if I tick perform test, it will create a path of this material, and it will get to this position here. And show coordinates just was for debugging, so it lets me see the coordinates of each tile. So as you can see, the yellow is the path from the player's start position, and we can change that. It won't generate a path if it's a wall that we if we try and generate a path to a wall, because that can't be found, or if it's an inaccessible location like over here, because there's walls surrounding that area. Okay, what's next? Okay, so I'll show off the parallel noise. So the scale is right now at 10. If I reduce that, it should be slightly more less noisy looking. So as you can see, it's more there's less walls, and I have a cutoff point here, so this is the height cutoff. It's at 5 currently. If I reduce this, we'll have less pathways for the player. So if it's on 2, it's more like a hill-like terrain, but then because there's less pathways that the player can get to, there's no objects being spawned because the player can't access any of them. So, and if I remove the height cutoff completely, so I set to 1, then of course it will mostly be hills and stuff, kind of like Minecraft. So yeah. And then we can offset this, so I can give it offset of 10 on the X, and it will all be moved along. And the player's starting position is the first available what's it called, tile. So the player in this situation now over there, instead of in the corner over here. So yeah, let me put that back to, I think that was on 0, and noise scale back to 10, and the height cutoff to 5. So the height cutoff is any pixel value used in the parallel noise that's below this cutoff or equal to it, equal or less than or equal, will be set to 1 automatically, so that it's a floor instead. So let me show off the code for this. So we'll start with the cell. This is each tile basically. So it has I call it mesh, but it's actually a prefab for the actual tile itself, so you can see it. Then it has a scene item. This is null unless there's an object on this tile. Then the scale, which is the scale of the prefab. Then X position, Y position. Then some booleans for is it a wall or does it have an object. This is for the Pathfinder to tell if it's a wall or not. And then there's the G cost, H cost, and F cost for the A* algorithm for calculating the cost to get to the tile itself. And then this is just the constructor, so that we can pass the X and Y position to it. And I can show off the parallel noise as well actually before I go to the terrain generation script. So this has a width, height, scale, X and Y offset, and those are all set in the constructor. And then we can generate the texture using the generate texture function I made. So it returns a texture 2D. So here it creates an empty texture. Then we loop through the X and Y coordinates of this texture, and then we calculate a color for each pixel. So the calculate color function takes the width and height that's passed into this object, which is based on the width and height of the terrain that we generate. It's multiplied by a scalar and added, the offset is added to it. And then we use the parallel noise mask function with these coordinates to generate a color value, and then we create a color using that color value for the RGB inputs, and that makes it a grayscale color, and we return that. That's returned here, and then we set the pixel to equal that color, and then we apply that texture, and then we return that texture when we're done generating the whole thing. Okay, and then in the terrain generation, this is the main bulk of the code, but I can show off here. So this is setting the player's start position. It basically finds the starting cell, it loops through and finds the first available one, and then it sets that to the player's position. And then this is the code that generates everything. So, so we loop through the X, we loop through the Y, and then we create a new cell object, and then we instantiate a terrain cell prefab and store that inside the mesh. And we give it a scale, and yeah, rotation is the identity, quaternion identity. And then show coordinates is just for showing coordinates. That's just for debugging. Then if I is equal to 0, j is equal to 0, or I is equal to scale x minus 1 and j is equal to scale y minus 1, then we are at the perimeter of the whole generated terrain. So we want to build a wall there. So we set isWall to true, and then we scale by 4 along the y-axis, and we give it the wall material. Okay, and then here I just, for extra aesthetics, I just make the corners even taller. Okay, and then if we're not at one of the perimeter tiles, then we get the color pixel from the parallel noise that we generate before we call this, actually. So I should have showed this off first. So this is the generate function, and then parallel noise texture, which is a private 2D texture, is created and by the parallel noise generate texture, and parallel noise is a private instance of parallel noise that I showed off here. Okay, so the color, we get the R value because we only need the color value and not the whole color. We multiply it by 10 so that instead of between 0 and 1, it's between 0 and 10, just so we can scale by that value along the y-axis. And then we use the cutoff here to set anything below the cutoff, below or equal to the cutoff, to 1. So it's between 1 and 10 basically. And then we, if it's above that value, then we just set wall is true because that's going to be a wall. And then we scale along the y-axis by pixel color, which is the value in the parallel noise texture. And yeah, that's it really. And this is just for making it look pretty. So we make every other tile a different color just so it has a checkered effect. And that's the main bulk of generating the terrain. So after generating, what do we do? Okay, so we start the object generation. So that is the object generation script here. So this takes a bunch of values. So it takes an array of objects, 2 arrays of objects, and so that's the collectibles and the environments, and then those are gonna be broken down further into the 4 categories that the coursework asked for. So okay. So generate objects, we loop through the X, we loop through the Y. We check, is it a wall? Well, we check it if it's not a wall, and this is the spawn percentage that we set in the inspector. So if it's not a wall, and the percentage is correct basically, so we want to generate an object, and the item count is less than our max item count. So our max item count is equal, it's basically 75% of the environment scale. So it's the scale X and scale Y multiplied together divided by 2 added to the scale X, scale Y times together divided by 4. Add both those together, make them an integer, and that's our max item count. And then, so if that's all true, then we use the A* algorithm, which I'll show off in a bit, and we find a path basically from our start X, start Y, and our current X and Y position. And the A* algorithm that I implemented returns the list of nodes, or in my case cell objects. It returns a list of those if it finds a path. If it doesn't find a path, it returns nothing, so it would be null. So if it's not equal to null, then we want to generate the objects. So what we do is it's basically 50-50. So we have the 2 array of objects, and we randomly choose between them. So we generate a number between 0 and 99. If it's less than 50, then we go for the collectibles section, and if it's greater than 50, then we go for the environments. And the object we choose from that array is a random index based on the random number generated between 0 and the length of that array. So yeah, we just spawn an object, then we add that object to a list, and this is the scene item object that we create. So this is the class that represents that object. Okay, and we increment the item count just so we know how many we have, and then we set this grid position to have an object, and we set this object to be referenced by that grid position as well. So this generates all the objects in the environment, and then we want to start clustering the objects. Let me see. So yeah, this is if we want to cluster. So if the cluster amount is greater than 0 and cluster enabled is true, then we create a new instance of the cluster class. Okay. Let me show this off then. So I didn't do this through the tutorials, I programmed this myself, so this is my own version of the k-means algorithm. Okay, where do I begin? So this is the constructor. It takes a number of clusters, a width and a height, and then a list of items. So this is all the items that are generated in the scene. And yep, so we have a cluster array. So this is a list of arrays basically. And this is for each cluster. So each array inside this list is one of the cluster centroids that's going to have, how do I say this? It's going to have all the items within that array, if that makes sense. So yeah, and then this is the midpoints. Yeah, so that's vector 2 array, and then all items equals items. So this is the list of items, and then we just, it's not random, but we place the midpoints to have starting positions. So midpoint 0 have this specific start point, 1 will have this one, 2 this one, and then anything past that will have this, and it's based on I, so this will always be different for each subsequent cluster. Okay. Okay, so generate clusters. So this is the whole algorithm here. So we have has midpoints changed, and this basically is a function that checks if the midpoints have changed. So it loops through the clusters, and it compares the midpoints with the previous midpoints, and if any of them have changed, it returns true, and if it gets through the for loop, so none of them have changed, then it returns false, and that will make this while loop basically end. So then we would have sorted all our objects into clusters. So yeah, so for each scene item in all items, we have a very high lowest value first, just so this works. Then for each cluster, we calculate the x and y distance, and then the final distance to to each cluster basically. Then we loop through all the distances of that item and find the smallest, which is the closest value, so we know which cluster it belongs to. We find which cluster that smallest value belongs to, and then we add that item to that cluster. Okay, and then for each cluster, we loop through the items that belong to that cluster and get the sum of all the x and y positions and calculate a new midpoint for that cluster. Yeah, and then we set it to that new midpoint, and then we confirm. Oh, this is after the while loop. So then it goes back around, it checks have the midpoints changed, and then it just repeats that over and over again until they're all sorted. Confirm one of each. This is basically this is what checks the part of the requirements that confirms that one of each object from each category is in each cluster. So as I said before, I have collectibles, chess pieces, environment, and key, and it basically checks to see that each cluster has one of each. So it loops through the clusters. For each item in each cluster, it will check if there's an instance that has one these tags, and then after it's looped through all the items of that cluster, don't need this line. It will check if these are equal to false, basically. So if any one of them is equal to false, then it will return false because it's missing at least one of these objects. And if not, then it will loop through all the clusters and it will finally get to this and return true. So if this returns false, it returns basically confirm one of each. This whole function, it returns the boolean confirm one of each, which back in our object generator, we have inside an if statement. So if it doesn't return true, then we destroy all the scene objects, we set the item count to 0, we clear the list of objects, and then we call the generate objects function again. So this happens again, and yeah, so it will basically generate all the objects again and then go through that whole clustering process again. And if it's equal to false again, it will repeat that again. And if not, then it will finish, and then all the items will be generated and we would have finished. Did I miss anything out? Let me think. Pathfinding. So this is just the A-star algorithm. This is a version I followed a tutorial online because I did it before the tutorial. So yeah, it's just the A-star algorithm. So it uses heuristics to figure out the fastest path to the endpoint that you give it, and it returns a list of cells. So this is how I can visualize it. This is how I can visualize it with that test that I showed at the start. Okay. Oh yeah, and I print out the clusters as well. I should show that off just so you can tell it's working. So let me enable clustering, and I'll keep it at 3. It might take a while to load. Sometimes it's quick, sometimes it's long. It just depends on luck, really, I guess. Okay, cool. That was fast. So if I go to the console, oh right, this is all the way up here. Okay, so cluster 1 start. This just told me this is the first cluster. This is the midpoint, the final midpoint from that cluster, and these are all the items inside it. So we've got a collectible, a key, an environment, and a chess piece. So we have 1 of each. Then that's the end of cluster 1. Cluster 2, here's the midpoint, and you can see it has 1 of each object as well. And then cluster 3, the start, this is its midpoint, and then these are all the objects inside it. And then cluster 4 as well. Yeah. Okay. Perfect. So let me just go through the brief quickly just to make sure I haven't missed anything. So generate content based on your choice of environment, set distinctive rules for asset incorporation breakdown, use a set of 8 unique assets which can be clustered under 4 categories, use arbitrary shapes, noise generation, yep, pathfinding techniques, yep, and clustering. Okay, that's everything I believe. So yeah, thank you for listening.